we look here and we say it has to satisfy. Oh, this is so annoying. God bless you. I think it does this just to aggravate me. Okay. Hopefully this is where we are. All right. It has to satisfy these two tests. It has to say n times p, and what does n represent? Sample size. Anybody remember what p represents? From back in chapter 4 when we did your binomial distributions?
Oh, man, I wish I did.
Probability of. There were two things that can happen. A success and a failure. So, yep, P is population otherwise, but P is our success. And Q is the probability of failure. We write these in probabilities. We can make a fraction, we can make a decimal, whatever they gave us. If you pass both tests, then we can assume that this is normally distributed. Before we had to say, was your population normally distributed? Or was n greater than or equal to 30? This is what we did for your central limit theorem. Okay, this one for your normal, to approximate a normal distribution for your binomial distribution, we have to check these two things. And then we're going to use the same formulas we used at the end of chapter 4. We're going to find its mean. You're going to know right away that this is a binomial because it has no mean. If you go to do a z-score, you can't. It has no mean until we find it. So that's one way you're going to kind of figure out which one am I doing. And I kind of left these two separated so that you could see which one does which. Now, here's your n times p test. This is why we do this. Okay, if I do n times p, and p is not greater than or equal to 5, can you guys see with that little glare coming in? It's in your book as well. If it is not passing the test, it is not approximating a normal curve. If, again, one of them doesn't, but the other one does, it's getting closer to a normal curve, but I still have a little skew to this. When I pass both of these will pass, then look how I approximate a normal curve. We kind of seeing this? So that's where the test comes in. If the test fails, we say, cannot use this. Now, granted, in the book, there's not going to be a lot of times that the test is going to fail or you won't have any problem to do. So we're going to test them anyway, knowing that they probably will work, except for the little example that they give us when they won't work. Same as the central limit theorem. So in example 1, and example 2, we're just going to test to see, can we approximate a normal curve? So you say, in a survey of 8 to 18-year-olds, I don't care about those numbers, of heavy media users in the U.S., 47% of them say they get fair or poor grades. That's pretty high. So you randomly select 45. What does 45 represent? And you ask them whether they get fair or poor grades. So what do we consider a success in this case? What? If they get low grades, C or below, that is considered our success in this situation. And what is Q?
3.37. No, 4.3.
Right? Am I wrong? 1 minus P. Okay, 1 minus P. If it's not a success, it's a failure. So we have two tests to make. n times p greater than or equal to 5, n times q greater than or equal to 5. So we take your 45 and we multiply it by your 47, and we say is this greater than 5. We take your 45, we multiply it by the 0.53, and we say is this greater than or equal to 5. And in both cases, they are both greater than or equal to 5. One is 21 point something, one is 23 point something. So therefore we can say, yes, this approximates a normal curve. And now you can, a normal distribution. Now you can find the mean, and now you can find the standard deviation. Okay? So, in the book, on page 276, once they said yes, they found the mean, n times p, which is the same as your original n times p, 21.5, and they found the standard deviation. You okay with that? Okay. This guy says, in a survey of 8 to 18-year-old light media users, means they're not using it as much as the heavy guys, they found 23% get fair or poor grades. You randomly select 20 8 to 18-year-old light media users, so N is 20. What's your P? 0.23. What's your Q? 0.77. Good. So when you do N times P, do they both pass? Which one fails? The P. Good. 20 times 0.23 will give us 0.46. That's not passing. It's will give us 4.6. Sorry, 4.6. That's not passing. Now, most of the time, if you kind of eyeball it, you can kind of figure it out, because if the small one doesn't make it, the big one makes it, all we care about is the small one. So always test the smaller percentage because it's the same n. So automatically just test your smaller percentage. If that doesn't make it, we don't have to test the other one. We don't care if it works or not. Yes?
Where do you get the 5 from?
The 5 is the standard thing they want us to test. The 5 says if you're greater than or equal to 5, you will approximate a normal curve. Here's your n times p, here's your n times q. When it's not quite 5, it's got a skew to it. And this one's way off because neither one of them are 5. So 5 makes us approximate a normal curve. That's just the rule. Okay. So you tell me if this approximates a normal curve. You read this, and you tell me if it approximates. Okay. Your n is 100. What's your p? What's your q? So n times p, is this greater than or equal to 5? 34, it's greater, right? Then doesn't n times q have to be greater? If this guy, the smaller one, is greater, the larger one has to be greater, doesn't it? So yep, we good. We approximate a normal curve. That's a test we always have to do. It's the same as when we did the central limit test. Is the population normally distributed, or is your sample size greater than or equal to 30? It was kind of invisible to you because they never really gave us a question that would stop us from doing anything, because obviously if they did, then we had no work to do with that problem. So the ones they give us, yeah, will always work. Now, you have a little bit of a problem. You notice when you make a normal curve, you make bars, right? Well, what happens in these bars is if we put the midpoints here, which we usually do, we know our bars can connect. What happens is your probabilities, your binomial probabilities are discrete. They're whole numbers. Your number line is continuous. It's a continuous number line. So to make sure that that bar from 4 and 5, your 4 goes here and your 5 goes here, there's nothing that's going to go in between. We have this little thing that we call correction for continuity. It's like just expanding that bar. It's like this. Did you ever put an air conditioner unit into a window? Like if you need to use an air conditioner unit in your window at home, right? You open your window, you put the air conditioning unit in. Is there like any gap, usually? And what do you do with your gap?
Fill with that wax.
You fill it with something, right? Sometimes there's a little, mine has little accordion that things that you pull out, and you hold them out like this, right? So what it does is it takes that gap up to your window. So we need a little way to bridge that gap. We need a way to connect the 4 and the 5. So what I'm looking at is this. If this is my number line at 4, 5, 6, my bars, this is 5, this is 4. There's nothing to connect these in between. I need to make a connection here. I technically don't get a bar. I technically get this. At 4, there's a line. At 5, there is a line. There's technically no bar because it doesn't go anywhere. I need to make them so that I can make a bar around each one of these and they will touch each other. So look where they kind of meet. They meet halfway, don't they? So if I could either add a half to something or subtract a half from something, it should take that slack away. I should make them meet, right? Now I won't change the probability of anything because nothing happens at a half a number. If I get 20 successes, I never get 20.5 successes. So what we do is what we call this, we call it a correction for continuity. And the rule is simple. Here's your rule. You're going to figure out where your numbers are, and you have a list of numbers. All you got to do is get that bar there. You're going to subtract 5.5 from the low end, a half. You're going to add 0.5 to the upper end. That's a half. But the key is to figure out where do I start, where do I stop. So this is the most important part of this whole thing, basically, besides checking that they work. So I want to say, what is the probability of getting between 270 and 310, and I say inclusive. What does inclusive mean? I include those numbers, so therefore equal to those numbers, right? I'm going to include them. If I'm not inclusive, I don't count those endpoints. I say in between, nothing else. Now, here's how you do this. Here's your start, 270, 271, dot, 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 309, 310, and I end. So my rule says, take the lower number and subtract 0.5. So if I subtract 0.5 from this number, what do I get? 265, sorry, 269.5, okay? If I add 0.5 here, what do I get? 310.5. So now, I'm going to go between 269.5 and 310.5. Will I ever find a 269.5? No, but the first one I will hit is 270, isn't it? So I'm good to go there. We're going to work with these in a little bit. We're just going to get where the 0.5 comes in. Here's another one. The probability of at least 158 successes. How do I say at least? Greater than or equal to. That's the least amount that I want. I want it to be that much and more. So if I go to start this, what's my starting number? 158, then 159. So if I'm going to correct this for continuity, what do I have to say? The probability that x is greater than what number? 157, whoops, 0.5. I'm going to drop the lower one, 0.5. So is the first one that I'm going to hit 158? The only time you're really going to see this is when we go to throw this in your z-score formula in a minute. The only effect this really has is I'm going to have to use this number and not 158. Now, what happens if it said the probability of more than 158 instead of at least? How do I write this probability statement? The probability of more than. 158, right? But it can't include 158, right? So what's the first number that I'm going to need to get? Okay, so just give me the first whole number first. You got it. It is 158.5. But what's the first? If I'm looking at my numbers and I'm going to string them around, do I take a 158 for this? So I'm going to start at 159, right? Then go to 160, then 161, dot, dot, dot. So like if you're dropping the lower half, all you're looking at is the lower half. If you're raising the upper half, we have no upper half here. It's continuous. So like Ariel said, that's where she got the 158.5. So she's going to change her probability statement to say greater than, 157.5. Oh, 158.5. I'm sorry. You said 158.5. So we're going to drop this guy down 0.5. Will we ever hit 158.5? What's our first number we'll hit? 159. Isn't that what our statement says we need to get? Greater than 158? Okay? So last one. Find a probability that x is less than 63. How do I say that? Less than 63. So I start here at the 0, the 1, dot, 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 61, 62. Do I include 63? It's got to be less than 63. So how do I change this for continuity? Drop the lower 1.5, raise the upper 1.5. So what's my upper boundary? 62. So what am I going to make this? 62.5. Will I actually use 62.5? Will I use 63? So the last one I will use is 62. It doesn't make a difference right now in your probability statement because you're still only going after whole numbers. But when we do your z-score, it will make a slight difference because that's the one we have to use. We have to correct this for continuity. So you guys try these two. Are there 2 or 3? These two. Set me up the original. All right, so the first one. My original probability statement is what? We can start with 57. Okay, less than or equal to because why? It's inclusive. So start like this. I started 57, dot, 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 dot. I ended 83. What's my corrected statement? 56.5. I dropped my lower end, 0.5. That's a 6. And what's my upper end going to be? 83.5. Will I ever hit a 56? I never hit a 56. Will I ever hit 56.5? What's the first number that I'll hit? 57. Will I ever hit an 83? Yes. Will I ever hit an 83.5? An 84? So I'm good. Okay? This is just applying this for correction. Now, what's the difference between that statement and the one I wrote? It's not closed, right? So how did you write that statement?
57, less than 83.
Okay.
And we hit a 57.5 less than, no, in between the thingy and the 82.5.
Okay, so let's see what happened here. So we said we can't include these. So what's our first number we can use? 58. Can we use 82? Can I use 83? No. So I take my lower one and I drop it 0.5. Good. I take my upper one and I add 0.5. Good. See the difference between the inclusive? Now, your probability statements with your 0.5s never have to have an equal sign on them because you will never get a 0.5. It's just now when we go use your z-score, when we say this, instead of saying 57, we will say minus whatever. We will say 57.5 minus blah, blah, blah. That's the only difference you're really going to see, is we just corrected that number for continuity. Because your area under the curve is 1. If you're kind of missing those little pieces in between, you're missing some of your area. So this just takes that little slack up. It's just like the air conditioning unit when it goes out to fill the window. It just fills the bar, technically. So how do I write this one? Probability x is what? Less than 54? Or equal to? At most. Can I have 54? That could be the most that I get. So I know I'm blah, 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 54. So your corrected one is what? X is less than. You don't really need to equal to. You can, it doesn't hurt it. Because you're getting a 0.5. You'll never hit the 0.5. If you want to leave the equal to because it's your original one, that's absolutely fine. So are we kind of seeing these?
The score you get is more like the difference between
Inclusive means the word include. So if I say, here's your numbers. If I say between 1 and 3, inclusive, that means I want you to include 1, and what comes between them? 2, and I want you to include 3. I want you to include those endpoints. If I say between 1 and 3, what number is between 1 and 3? 2. I can't include 1. I have to say inclusive. That's where your equal signs, less than or equal to, comes in versus just your less than. This one would say is 1 less than x less than 3. What number falls in between there exactly? And we're only using whole numbers right now, so that's why it's a little tougher to see. Normally your number line would say from 1, open it, all the way to 3, open it. However, because these are discrete, we don't have this situation. We only have a 1, a 2, a 3. I'm not using this, not using this. My only whole number is 2. Without having a continuation, it's a little tougher to see. But that's where we're correcting continuity. So it makes a little bit more sense? Okay. You guys have any questions?